Okay, so here's our review for the end of chapter 8 and chapter 9. So I will include chapter 8 that we hadn't covered in the previous test. So we have L'Hopital's rule, which says that if you take the limit as x goes to infinity of f of x over g of x, and if that's indeterminate, so you have to have a ratio, that's indeterminate, it's the same as the limit as x goes to infinity of f prime of x divided by g prime of x. So we applied this to some simple cases that we had indeterminate results for back in chapter 1. Where it turned out to be more useful was where we had two functions that were somewhat different. Let's say x squared over e to the x. And if you plug infinity in there, you've still got infinity over infinity, which is indeterminate, but we can't use any of the canceling out techniques, the rationalization, squeeze theorem. So what you do is you take the derivative. So you've got to know how to take derivatives. And so you get 2x over e to the x. Now if I plug infinity in again, I'll still get an indeterminate result. So you can use L'Hopital's rule as many times as you need to get a determinate result. So ultimately here, if we take the derivative of the numerator, we get 2 derivative denominators e to the x. So now we can plug it in because we get 2 divided by infinity, which is 0. And that comes down to the fact that e to the x function grows much more quickly as x gets large than compared to x squared. So I'll give you something similar to this kind of situation. You may have to use L'Hopital's rule more than one time. And if I gave you e to the 2x here, this would be 2e to the 2x, the derivative. So make sure if I put a little twist in there with an exponent other than just x, there's some multiplier by the argument. Make sure you know how to do that, because we've had problems with that in the past. So I might just throw that in there just to make sure you're learning things. Then you have improper integrals. Now these are important by themselves are important, but they're important because a lot of times integrals that you use the integral test for are indefinite integrals, because if you have an infinite series, you're going to have the limit is going to be infinity. The key thing here, what I want you to remember, is that if you have the situation where you go from 1 to infinity of something, let's say 1 over x dx, what we need to do is rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. So we replace the upper limit with b, which we assume is finite to start with, and then once we have the expression, then we can take the limit as b goes to infinity. So in our case right here, we would integrate 1 over x dx, which is the natural log of the absolute value of x, and we'd evaluate that between 1 and b. So that's a little different. It's kind of like a definite integral, but it's got a variable as one of the limits, but you still do the same thing. You plug in the upper limit, subtract plugging in the lower limit. In this case, the natural log of 1 is 0, but even if you didn't know that, you know the natural log of when you take the limit as b goes to infinity, the natural log of infinity is still infinity. So what you get is infinity, or I also want you to make sure you use this word diverges. So if it equals infinity, don't just say it equals infinity. I want you to say it diverges, because nothing really equals infinity. So this is a more correct way of doing it. You know, there was that tricky one where you had to use L'Hopital's rule within an improper integral, but you know that's going to take too long. So it'll be a fairly simple one. It'll be probably a polynomial of some sort, maybe 1 over square root of x, 1 over x, 1 over x squared. One of those varieties. You know, the other option is if instead of the limit going to infinity, if the function goes to 0. So if we did the integral from, say, 0 to 1 of, what are we going to do here? 1 over x squared dx. So what happens here, the limit doesn't go to infinity, but the function goes to infinity at this limit, at this lower limit, and you would actually, you know, go from 0 plus, because this function does not exist exactly at 0. So again, you would replace the lower limit in this case, because that's where the function goes to infinity, with b, and then you would take the limit as b goes to 0 from the positive side of 1 over x squared dx. You know, you can do the rest of that if you want to work out an example. We did it in class. Okay, so that's chapter 8. Now, chapter 9. So what I'm going to do there is I'm going to give you 4 or 5 problems that are different series using different tests. Now, I'm not going to ask you to figure out which test. I'm going to tell you which test to use. You just have to know how to apply the test and write it out correctly. So, you know, we've done that many times in class, in videos, where you, you know, you say this series converges or diverges according to the convergence criteria for this test. You specify the convergence criteria. You show how that the particular example satisfies or doesn't satisfy the convergence criteria, and then you know, you've seen a lot of examples, so go back and look at what we did. So I'm not going to go through every particular kind of problem, but you do have that sheet that you'll be able to bring in, so it's just a matter of making sure you understand, given a particular test, how do you apply it. And we went through a whole bunch of examples with that handout. So you're just going to have to study the handout. I'm not going to narrow it down for you. You know, most likely there's going to be a geometric series of some kind, or a p-series. Okay. Now, we also spent a lot of time on radius of convergence and interval of convergence. So again, I'm not going to go through a specific example. Just give you the basic idea so you understand what we're doing here. So you take the limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. And we see where that is less than 1. So this typically allows us to figure out the interval of convergence except the endpoints. So we use the ratio test. This is the ratio test. If there's an alternating series, then the absolute value kind of gets rid of that. So we don't have to worry about the alternating series. So we, substitute in for n plus 1, take this ratio, we rearrange all the terms, and we end up with something, the absolute value of something is less than 1. And then we rewrite this. So let's say it's x minus 2 over 2, something like that. So what we do is we change this absolute value into taking this number 1, we make it negative 1, we take away the absolute value signs. So we have x minus 2 over 2. Put that in there, then you multiply both sides by everything by 2 to get rid of the fraction, and then we add 2 to get that. So this is the interval of convergence, except you got to do your endpoints. So what you're going to do there, of course, is you're going to plug in x equals 0 and x equals 4 and simplify the original expression so that you don't have x in it anymore, you just have n, and it should simplify down to, most likely, a lot of times, one is an alternating series, one is a non-alternating series. So you just have to apply the alternating series test, and a lot of times it's a p-series. It could be factorials could be involved, how to simplify factorials. So remember, what's an example here? Oh yeah, so also if you have negative 1 to the n times something like negative 2 to the n, remember that is negative 1 to the n times negative 1 to the n times 2 to the n. So you break up this negative into a negative 1 to the n and then the positive term, and when you combine those two, you can add the exponents and you get negative 1 to the 2n times 2 to the n. And so in this case, you have to think about, are there under circumstances where this is either always odd or always even, which is, in this case, it's always even, because any integer multiplied by 2 is even. Odd numbers multiplied by 2 would now become even. So this would end up being just 2 to the n. So you have to think about that kind of simplification. Now, if you plug in the other side and you end up with positive 2, then you still have this alternating part. So this one here, negative 2, would become a non-alternating series. But if there's positive 2, then it would be an alternating series. And alternating series tend to converge more readily than non-alternating series. So again, I'm going to ask you for the radius of convergence. In this case, the radius would be 2. It's not the total distance, but it's the distance from the center point. So the center, the center here would be x equals 2, and so it's plus or minus 2. But we would say the radius of convergence is 2 for my particular example. And my interval would be from 0 to 4, and I'd have to check out the endpoints. Since I didn't give you the function, you'll have to figure it out yourself. I want you to derive a Maclaurin, hopefully I spelled that right, it's probably wrong, or Taylor series for n terms. I'm not going to ask you to try to figure out the equation because that takes a little finesse and a little bit of practice. But the Maclaurin series says that the function f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of x times x cubed over 3 factorial. And we did that in class. Remember, we did e to the x, and we did probably the sine of x. We might have done the cosine of x. So those would be good ones to know how to do, to go back and look at that. I could also do e to the 2x, just make it a little bit so it's just not cookie cutter. So you could take the derivatives, these, you just get this extra factor of 2 that keeps popping up. So that's the Maclaurin series. The Taylor series, it's very similar, except it's f of c. This is where we're centered around x equals c, and it's f of c plus f prime of c times x minus c plus f double prime of c times x minus c quantity squared over 2 factorial plus f triple prime of x times x minus c cubed over 3 factorial plus dot 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 dot. Continue that on. So that would be a Taylor series where you're centered around. It's a Taylor series when x is not equal to 0. Here x equals 0. So this defaults back to that if you put 0 in there. So I just want you to be able to, make sure you can take the derivative, multiple derivatives of this however many times I need to. I won't give you anything more complicated than that. Most likely I'm going to give you one of these just so you can have practice at making sure you deal with that 2 multiplier in front of it. I think that is it. I believe it is it. Let me just pause and think about that. Okay, so yeah, I've looked at everything, and I would say that that's all you need to know. I guess one more thing. I just thought of it. Hopefully you didn't hang up there. Make sure you can calculate the sum for a geometric series. So that's the sum is a over 1 minus r. The ratio is r. So look at that. If I give you a geometric series, I will probably ask you what the sum is. Now for the other ones, except for the telescoping series, we usually don't know what the actual sum is. But for the geometric series, we do.